and how are you today?
Good.
Good, okay. So let me draw a tree, okay? A binary tree, yeah? We know the binary tree. What does binary mean?
2.
Okay, 2. It means that any node in the binary tree can have at most how many kids?
2 kids.
And every node except which node does not have parents?
Root.
Okay, and how many parents does one node have? Except the root.
1.
Yes, okay. And then a binary tree is also a graph, yeah? A graph.
Yeah.
And it doesn't. Binary tree is actually, how do you call it? A cyclic undirected graph. Undirected graph.
Undirected graph.
Okay. Graph. Okay. A cyclic means does not have cycle. It does not have this kind of cycle. Okay. Yeah. Undirected means the edge does not have direction. Okay. So it does not have a direction. Yeah. So it's a undirected graph. Okay. Undirected graph. Undirected graph. Probably AUG. Okay. I don't know what's the initials. Okay. But anyway. So this is a binary tree. So how about if I tell you what kind of binary tree is this one? Every node, every level is the first level has one node, which is 2 to the power 0. The second level has 2 node, which is 2 to the power 1. The third level, which is 2 to the power 2. Yeah? Yeah? So that's how many? When you add it together, 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 equals what?
2 to the power of
3 minus 1. Okay? So basically, if there are n levels, how many nodes does this tree? We call it full binary tree, yeah? Full, because it's full, yeah? You can't, if for level 3, you can't have any more nodes, right? The maximum binary, maximum nodes of a binary tree, which has 3 levels, has how many nodes? Come on, count. How many nodes?
1, 2, 8. No, 7.
7. That's what I'm saying. And how about for n equals 4? How many nodes?
15.
And no, n equals 5.
30.
30 what?
Wait.
2 to the power of 0 plus 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3 plus 2 to the power 4 plus 2 to the power 5 equals what?
Wait.
What does this equal? If
31. No, just 30.
31 is correct. Come on.
31. Yeah, 31.
Yeah, because it's 2 to the power of 6 minus 1, yeah? So look, 2 to the power of 0 plus 2 to the power 1 plus 2 to the power of n equals what? Equals 2 to the power n plus 1 minus 1. Okay?
Yeah.
Look, when n is 2, this added together equals 2 to the power 3 minus 1. Does it make sense?
Yeah.
This is called full binary tree.
Yeah.
How about if not particular full binary tree, you can have a few nodes missing, particularly on the right. Okay, so if I erase that, what does this call? Okay, complete binary tree. So it's complete, but not full. When it's full, every node is full. But you can erase some of these. Look, this is also a complete binary tree, but this is not, right? If a node is missing, it has to be on the right hand side, right? Look, this is not a complete binary tree, okay? All right?
Yeah.
So, okay, the question is, given a binary tree, how do we check it's a complete binary tree? Okay, so let me do this, okay? So, look, this is a complete binary tree, also a full binary tree. And is this a complete binary tree?
Yeah.
Yeah. Is this?
Incomplete.
Yeah?
Yes.
Yes. Is this?
No. Yeah.
Yes. Is this?
No.
Is this?
No. Yeah.
No, because look, there's missing here. Come on.
I said no.
Yeah. So if the missing node, it has to be on the right hand side, right?
Yeah.
Do you get it? Yeah.
Yeah.
Okay. Another one. Wait. Okay. Is this?
No.
No, because every level has to be full except the last one. Yeah.
Yeah.
These n minus 1, it has to be, all the nodes have to be occupied except the last one.
Yeah.
And even the last one, it has to be on the left hand side, as left as possible. Okay.
Yeah.
Okay. So, any idea how can we do this? What kind?
Breadth search.
Wow, well done. Breadth search. What's breadth search mean?
Level by level.
Level by level. And how are we using this breadth search? How are we using this breadth search?
Cube. Well
Yeah.
done.
Yeah. So we are using a
Well
cube.
done.
So in Python, what kind of data structure are we using? I mean, what kind of
DQ.
DQ? What does DQ stand for?
Double-ended. Yeah.
Yeah,
Double-ended Q.
Okay, so yeah, we're using the queue binary search level by level. So what's the sort? How can we check if it's a complete binary tree?
Oh, we just look at the last one.
Look at the last one.
And the others. And you just if we others are just
We're going on
complete.
hunt
Sorry.
on Thursday.
Sorry.
If okay, so
Can you tell me how you do it? Yeah, just any thoughts would be nice. Any thoughts would be nice. So how? Yeah, level by level. But how are we checking? How are we validating?
we're checking level by level.
Yeah. Then how do we check level by level? For example, if this is not a complete binary tree, so you travel here. Right. 1, 2, 3, 4, 5, 6. So how do you know it's not a complete binary tree? You travel 1, 2, 3, 4, 5, 6. So how do you know it's not a complete binary tree? Any idea how we're doing this?
Okay, so
I give you a hint.
the second
Okay.
one is full and the last one is not. So that's okay.
The second one is for which is the second one?
This one.
The second one is what?
It's
4. Yes, okay, yeah. But the last one, look, how do you know it's
the last
level? Yeah.
yeah. Okay. Then
Yeah. Any idea? Any idea? Just any idea? This is a bit tricky. Think about it, people. Ryan, think about it. How are we dealing with that? Yeah, it's breadth search, but how do we know if a node? I mean, so basically we want to look for the empty holes here, right?
Yeah.
Am I right? If there's an empty hole, yeah, if this should be empty, this is empty, yeah? If it's an empty hole before we reaching the last one, then it's not a complete binary tree, yeah? So look, we level by level. But look, when we visit here, it's empty, yeah? But it's not supposed to be empty, right? Yeah, right? Look, for a complete binary tree, complete binary tree, you walk level by level, yeah? And it's always valid, not empty. When you reach the end, that's fine, right? Alright? But look, if there's a hole somewhere in between, look, 1, 2, 3, 4, and then look, these are holes, yeah? Then it's not a complete binary tree. Does it make sense? Yeah? So we need to have a Boolean. You know what's Boolean?
Pudding, yay!
Boolean. What's this mean?
Pudding.
Yeah, Boolean.
Believe
You say
True or false? Boolean. Yeah, binary. True.
You lean to a boo.
So we have a hole.
Yeah.
Yeah, we have a hole. We set the hole to false. Then if we meet the empty hole, we set it to true, right?
Yeah.
And then when we meet the node, if there's a hole before, then it's not a complete binary tree. Am I right? Does it make sense?
What do you start on?
So look, if I will perform this binary search, by breadth search, level by level. But when I meet the hole, I noted, okay, I have already meet the hole, yeah? And then the next time, when I keep going, if I meet a node, what does it mean? There's a hole before the end, then it's not a complete binary tree, right? Does it make sense?
Yeah.
Okay, so look, I give you an example, okay? Okay, let's label it. Let's label it. 1, 2, 3, 4, 5, 6. Okay? Q, yeah? Q, what's Q? First in?
First out.
First in, first out. And what's the first in, last out?
Stack.
Okay, good. Look, the Q we initialize with which node?
Root.
Which is
1.
1. Okay, so we repeat. While the Q is not empty, okay? Yeah? Alright? I mean, look, while Q is not empty, we dequeue 1, right? We dequeue, yeah? Dequeue, which is pop left. I take it out, yeah? At the beginning, I set the hole to false, okay? Because we haven't met any hole, okay? Right? Yes?
Yeah.
I take 1 out. What should I push?
2.
2 and 3.
3.
2 and 3. Okay, so next one to take out.
2 and to push 4 and 5.
Why there's empty, why there's element in the queue, I keep doing this, yeah, okay? And what's the next to take out?
3.
3. Okay, look, this is the interesting part. I push the empty node here, so I need to push the empty node, right? Look, previously we don't need to push in the breadth search, but now I need to push the empty hole. So I push the empty hole, which is I do it empty. Okay? Yeah? Okay, what and push the 6 in, yeah?
Yeah.
Right? And push the 6 in, okay? Are you okay? Push the 6 in and look what's next to take out.
4.
Okay, what's its kit? Nothing, yeah? I push nothing in. Okay? And then what's the next R?
5.
And then also pushing two nothing in, yeah? A hole, yeah? Okay, now
Somebody else could go into C.
I take it, I meet the hole, yeah?
Yeah.
I meet the hole. I take it out, but I set it to true. Right? Yeah? Yeah?
Yeah.
Okay, so next, if it's empty, I don't expand the kit, yeah? Because empty does not have a kit there. And what's next? What's next? What's next here? The next element of the queue.
6.
6. Okay, look. I mean the non-empty node. But look, it's true. What does it mean? It means that there's a hole before 6. And I return false, right? Yeah? It's not complete binary tree, am I right?
Yeah.
Yeah? So I can keep doing. If there are 5 here, right? This is still false, right? Because and then you put another 5, it doesn't matter. So you have plenty of these empty, but which you take it out, but you don't expand any kits, and eventually the queue will be empty, and then at last you return what? You return what? In the happy case, true. Yes. Does it make sense?
Yeah.
Okay. So the key thing here is we expand. We push the empty node in that as a placeholder to for next time if we meet the empty hole, we set this hole to true, right? Am I right? Yeah.
Yeah.
And then when we meet the node, if we have no and there's a hole before, then we return false immediately, right? Does it make sense? Should we do it? Define complete binary tree, okay? Binary tree is complete binary tree, okay? Root and
The column! Yeah.
if If root is empty, what happens? If an empty tree, we call it what? We say it's a complete binary tree, yeah? Does it make sense? Okay, it's a very special case. So if it's a empty tree, we call it a complete binary tree, yeah? Yeah?
Yeah.
Okay. Okay, so now what should we do next? What should we do next?
Put the root in the Q.
Okay, so Q equals DQ, yeah?
Yeah.
And a list of the beginning we put the root in, right? And we also have a whole, which I set to true or false.
False.
Yeah, well done. So now I keep doing this. Breakfast search, yeah? Y, Q, yeah? Or Y length Q bigger than 0. It's the same thing, yeah?
Mm-hmm.
I take a Q out, P. Current node, okay? Current node P, okay? Equals Q dot what? Q dot what?
Q dot pop.
Pop what?
And pop.
Pop what?
Left. Calf. Yeah.
So if P is none, if current node is none, what should we do? What should we do? We set a whole to what?
True.
Okay. Else what?
Hold.
Else what? Else what? So else we need to push the kids. So look, if P is not none, it means we current node we have meet the current node. But in this case, if whole is whole, if there is a whole, what should we return? Should we return what?
False.
Yeah, return false. Look, remember, if we meet the whole and now this is the valid node. There was previously a whole before and now we return false. And then now next we need to append what? P dot append what?
Q.
Q dot append P dot what?
Left.
Left.
Right.
Left.
The next right.
Q dot
append the P right. Oh yeah.
Yeah, P dot right. And then what's missing?
Return.
Return what?
True.
What's the time complexity?
N.
What's N?
The number of nodes in the binary tree. Yeah.
What's the space complexity?
O. N.
Why is
Because
it
we're using a Q.
Using a Q.
DQ.
Additional space to store the nodes, yeah?
Bye.
Store the nodes, okay? Does it make sense?
Yeah.
Okay,
Nice.
Find a missing piece. Yeah. Find a missing piece.
Find the multiple types. P equals Q. Q dot pop left.
Pop is lowercase, not uppercase. It's case sensitive, okay? You know case sensitive. Uppercase and lowercase are different, okay? Oh, that's a very small p, okay? Okay, pop left. Okay, and what's next? If p is none, what should we do? If p is none, what should we do?
Out.
If we set the whole to what?
False.
Yeah, yeah. Come on, understand it. Come on, why? Yeah.
N equal false.
Not and whole. This is different than what I wrote in the notes. I'm just checking if you understand, okay? Not copying my notes. What? It was what?
True.
Yeah.
Yeah.
Does it make sense? Yeah, right?
Yeah.
Because at the beginning whole is false, we haven't made a whole. And now if P is none, it means we have made a whole. And if P is not empty, if there's a whole, we return false.
Yeah.
Otherwise, we push the kids to the back of Q. And when the Q is not empty, we dequeue, yeah? We take an element at the beginning of the Q, yeah? Does it make sense?
Yeah.
Okay, that's it for today.
I will smash.
Say bye-bye and see you tomorrow.
Bye.